So let's say that you go to a restaurant, and on the restaurant menu, so I have two different restaurants here. We're going to just look at this restaurant first. On the restaurant menu, it's a pretty limited selection, okay? There's 2 drinks for you to choose from. There's 3 sandwiches for you to choose from, and there's 3 desserts for you to choose from, okay? Now let's assume that at this restaurant you choose one of each. You're choosing a drink, a sandwich, and a dessert, okay? None of this like, oh no, I don't do desserts, or just tap water, please, okay? You're going to choose one of each of these. How many different meals can you make from those 2 drinks, the 3 sandwiches, and the 3 desserts then? So Curtis thinks he knows. I want everyone to take a couple of minutes, talk about it in your group, think about it, see how many meals do you think. If you need to list them all, list them all. Okay, so what do we think we have? Anybody have an idea? I got 2 people who told me what they think. Anybody else? Cassie, what do you think? 18? How many people are thinking 18 different ways? Okay, so how did you figure that out, Cassie? Just like the trumpet kind of one, right? Okay, so you said drinks, D1 and D2 for the drinks, and S1, S2, S3 for the sandwiches. Oh, and I guess for desserts we need something else for that. We can't use D again. And then combine them, okay? So that's one way to do it. And then list them all. So just systematically list them. Another way we can do it is called a tree diagram. You've probably seen these before. So we have drink 1 and drink 2, okay? And then for drink 1, we have 3 choices of sandwich. So sandwich 1, sandwich 2, sandwich 3. And then we have sandwich 1, sandwich 2, sandwich 3. So notice now we have 6 possibilities because 2 drinks and 3 sandwiches. And now each of these sandwiches we have 2 choices for dessert. Oh, 3 choices for dessert, sorry. Thank you. So we'll call that D, we'll call it I don't know, ABC. Apple pie, banana cream pie, and coconut pie. No, chocolate pie. Let's just say chocolate. Any chocolate works for me. Okay, so you can see if you count those all up, you get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Okay? Everybody okay with that? Now, how could you do it really quickly? What do you notice about that 18 number and how it relates to those? They're just multiplied, right? It's 2, because you have 2 choices at the first level, then you have 3 choices at the second level, the sandwich level, and then you have 3 choices at the dessert level, so it's 18. Okay? So this is like, the food truck outside. Even a food truck has more selection than that. I don't know. That's, I don't know. Now you're at a more upscale restaurant where you have a choice of an appetizer or an entree or a dessert and a drink. And if you choose one of each of those 4 categories, how many different meals can you make at this restaurant? Well, we don't want to do a tree diagram, right? That's going to take us forever, and it would use a lot of paper as well. But we can use this method where we just multiply 10 times 20 times 20 times 5. What does it work out to be? 20,000. So there's 20,000 different meals to choose from, and that's not including the option of not choosing a dessert or not taking an appetizer, okay? Or sharing 2 appetizers. That's just one of choosing one from each category, okay? And that's the fundamental counting principle. The fundamental counting principle is on page 688. So I'm not going to write it out for you, but if you look in your textbook on page 688, you will see that it says if there are n different objects in one set, n1 different objects in one set, and n2 different objects in a second set, then the number of ways of choosing one object from each set is n1 times n2. And if we have a third set that we're choosing from, we're going to multiply by the number in that set. So every time we are picking something from another set, we just multiply by how many picks, how many choices there are in that set. And that's the fundamental counting principle. Make sense? So it's just multiplying, so that math is kind of easy. Where it gets tricky is when we introduce all the other stuff that's coming up in Chapter 8 is knowing when we can use this, okay? But the big thing with the fundamental counting principle is that we are saying and. We want to pick a drink and an appetizer and an entree and a dessert. So then we just can multiply by the number of drinks, the number of appetizers, the number of entrees, the number of desserts. Okay? Questions for me? So we'll do one other example. I think I'm just going to do one with you. And then we'll look at 8.2. So how many 3-digit numbers can be formed using the number 0, 1, 3, 5, 7, 9? So where is this kind of an important question that comes up? Where in real life might you be interested in figuring out how many different ways can I arrange 0, 1, 3, 5, or choose 3 digits from 0, 1, 3, 5, 7, 9? Did I hear someone say something? What about passwords or PINs? Right? How many of you are, you have on your bank card, you can have up to a 6-digit PIN, but they tell you that if you want to take it down to the States, that you should have a 4-digit PIN, okay? So a 4-digit PIN, you've only got 10 digits to choose from on the keypad, so we could figure out how many possible PINs there are, but we'll save that question for now. This is a little bit reduced because I'm not giving you 10 numbers to choose from. I'm just giving you the odd numbers, 0, 1, 3, 5, 7, 9, the odd numbers plus 0. Okay? Now, if we're allowed to repeat numbers, and I only want a 3-digit PIN here, how many choices have I got for the first number? There's 6 numbers, right? So I'm going to choose one number, so that's 6 choices. And now I'm going to choose another number, and I'm allowed to repeat. So how many numbers am I going to have? 6. And then I'm going to choose another number, and I'm allowed to repeat. So I'm going to have 6 again. 6 times 6 times 6 is 216. Is that what it is? Yeah. Okay? So there's 216 ways of making a 3-digit passcode from those numbers if I'm allowed to repeat. Now, if I'm not allowed to repeat, okay? If I can't repeat any of the numbers, then how many choices? Yeah?
150.
How'd you get that? Right, so we've got 6 choices for the first number, but then the number that I chose here, I no longer have available to me, so I only have 5 choices for the next number. And now neither of those 2 numbers are available to me, so I only have 4 choices for the next number. And so I have 6 times 5 times 4 is only 120. So there are fewer choices if I have no repetition allowed. Okay? Questions? Does that make sense? So how many possible 4-digit PINs are there? If you're going to make a 4-digit PIN for your bank card, how many possibilities are there?
10,000.
How'd you get that?
10 times 10 times 10.
Times 10 again, right?
Yeah.
So you've got 10,000 possibilities, which isn't a lot. If you think about how many people have bank cards, there's a lot more than 10,000 people that have bank cards, but they each have maybe a different bank, right? There's Scotiabank and Bank of Montreal and Royal Bank and Credit Union and the Toronto Dominion. I mean, so there's that. And then everybody has their personal client number on the card too, which there's a lot of numbers on there, so that really distinguishes. So it's possible. It's unlikely, but it's possible that 2 people in this room have the same PIN on their bank card, but it's not likely that that's going to be a problem because you have a different bank card number and a different bank account number and so on and so forth. Okay? But if you were going to design a computer program to try to guess someone's PIN, if you stole it and wanted to use it, it wouldn't be that hard to guess 10,000 different iterations, right? But banks have a system where if you put in too many codes, they will take the card, right? So you can't guess 10,000 times. But you can see that, there's this war out there between the security of all of our information and then the people who are trying to get all that information. And it's just a matter of who's got the better technology. Okay, what about this one? Many passcodes on the computer, and on the computer now, right, they will say a minimum of 6 characters. You got to use a special character, you got to use capitals and small letters, you got to use numbers. That's all just happened in the last 4 or 5 years. It used to be a lot more flexible, but they've realized that they need more options for passwords. When more and more people are signing up for Instagram, for example, then we need to have more than 10,000 possible passwords for Instagram, because that's one program. And it doesn't have any other way of distinguishing between you and someone else. Okay? So let's say this is an easy one. 6-digit code, numbers or letters, repetition is allowed. How many possible numbers or letters are there? 36. Right? Because there's 10 numbers and 26 letters. So you have 36 to choose from for the first letter. And if you're allowed to have repetition, then you're allowed that 6 times. So it's 36 to the power of 6, whatever that works out to be. It's a pretty big number. But it's not big enough for some programs, right? Some programs, they want you to add characters in there and distinguish between caps and non-caps and so on. Okay, I lied. I do have one more question for you. Okay? Let's say you're writing a multiple choice test, and there are 5 questions on the multiple choice test, and it's that one of those kind where we give you just A, B, C, D, 4 choices per question. Okay? When I'm making up the key for this test, how many possible keys could there be? How many possible keys could there be? Or another way to ask this question, which I hate to say to you guys because I know you never do this, if you were to randomly guess on each of these questions, okay, how many different ways could you guess 5 questions with 4 choices each? And this is a fundamental counting principle question, because what I'm asking you is, how many choices have you got for the first question? 4. And how many choices have you got for the second question? 4. And for the third question? And the fourth question? And the fifth question? So it's 4 to the power of 5, whatever that works out to be. So for me, if I was going to make versions of this test so that it would be different every time, I have 1,024 versions I could make just by scrambling the multiple choice questions, or where they are. Okay? So that you couldn't memorize them. I could give every grade 12 student the same test, but it would be a different combination of letters. A, B, C, D, A, B, C, D, C, B, A, D, C, A, and so on. Okay? So you couldn't look at your partners and just copy what they had written as far as the numbers go. All right. Questions about fundamental counting principle. It's fairly straightforward, but when it will get difficult is when to use it. And so we'll keep talking about it. And we're going to use it again now. But if you could look on page 696 at the GS and the CU in 8.2. You will have time today to practice both of these. And you'll be okay with it. That's not what I want. Okay. So this is the important part about a permutation to remember, is that order matters. Okay. So we're talking about an ordered arrangement of objects. Okay? So let's say I have 3 students. Let's say I have Anna, Giano, and Henrik. And I want to stand them in a line. Okay? Because we want them in a line. How many ways can I line them up? 9 ways? 6 ways? Any other possible choices there? Options? Guesses? One of those 2 numbers is correct. 6 ways, right? Why is it 6 ways? Because for the first student, how many choices have I got? 3. Now that's students in line, so how many have I got left to line up? 2. And now I only have 1 student left, so I have 6 students to line up. Okay? If I have the letters in the word compute, how many ways can I rearrange those? So the question is, how many letters have I got altogether? 6 or 7? 1, 2, 3, 4, 5, 6, 7. So the first letter, I have 7 to pick from. Then I have 6 to pick from, and then 5, and then 4, and then 3, and then 2, and then 1. So when I multiply all those out, what do I get? 720? Okay? So 720 ways I can rearrange all those letters. They're not always going to make words, but that's not what I'm asking you. I'm just asking you to rearrange those 7 letters. So I have 720 ways I can rearrange them. Okay? Now that's kind of long and time consuming. That's looking a lot like what we were doing in the get started in the warm up. So we have notation that we use to simplify just the writing of that. And you may have seen it on your calculator and wondered, what is that all about? That exclamation point on my calculator is called factorial notation. Yeah?
It's 5040.
5040. Okay, I thought that may have been a little bit small.
Yeah.
Does that seem better? 6 times 4 is 120. Yeah, it has to be bigger than 720. Okay, I didn't think it was right. Oh, 6 factorial 720. We just forgot the 7. Okay, so if you put that into your calculator, so here you put this into your calculator, 7 times 6 times 5 times 4 times 3 times 2 times 1. Find the exclamation mark on your calculator and do 7 times. Now, here's the interesting thing. If you're not using a graphing calculator, the exclamation point is usually fairly easy to find. The graphing calculator also has the exclamation point, but it is not as easy to find. It is buried in one of the menus. So let me show you where that is. There we go. 7 we're going to type, and then the factorial button is under math. Num. Is it num? Wait. Yeah, all the way there, all the way to there. Okay? So math, probability, that's what that stands for, number 4. So that puts the exclamation mark in, and then we hit enter, and we do get 5040. Okay? I don't know if there's a way to set up shortcut keys on the TIs. No one's ever told me if there was, but I don't think there is. But if you learn how, tell me. Yeah?
I don't know if you can shortcut like functions, but you can shortcut numbers. So like for physics, like the constants, you can shortcut those. So it's like alpha G.
Oh, you can save them. Yeah, you can save them as A, B, C, D. But yeah, I'm not sure about the functions themselves. Yeah, good point. Okay? So 6 factorial, if you put that into your calculator, that's when you get the 720. 1 factorial is just 1, right? That makes 1 factorial is just 1 stop, okay? 0 factorial by definition is equal to 1 as well. So that's an interesting one. We need that definition of 0 factorial. It seems weird, but that's how it is. And if you put 0 factorial in your calculator, it should spit out 1 if your calculator is programmed properly, okay? And then, so n factorial is n. So we always start with whatever that number is, and then the next number down, so n minus 1 is 1 less than that. Then the next number down is n minus 2, n minus 3, n minus 4, and so on until we stop. We always stop at 1. You never go into the negatives with factorial. Okay? Once you hit 1, you stop. So 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. Okay? So the dot, dot, dot means we could have numbers in between, or we might not, right? If I have 6 factorial, then this is 6, this is 5, this is 4, and then we go 3, 2, 1. Okay? All right, I want to talk a little bit more about that fairy situation, because the fairy situation is not a factorial situation, right? We had 4 roots, And we didn't choose all 4 of them. We only chose 2 of them. But what we actually did is we took all 4 roots, or how we can think of it. We only chose the 4 and the 3, right? The going there and the coming back. But if we want to use factorial notation, how do I get rid of the 2 and the 1? How did you do it in the get started? Divide by the 2 and the 1. And so that gives me the 12. So if I had 5 roots, I could do 5 factorial, which is 5 times 4 times 3 times 2 times 1. And then what would I want to divide by? Because I need to divide by 3 times 2 times 1, and that is 3 factorial. Okay? So this is a situation where I have X number of choices, 5, but I'm only going to pick 2 of them. Okay? So it's 5, pick 2. And that's how we would do it. And we have a notation that allows us to shorten that down a little bit. Okay? So this is all about notation today and how to use it. So if we have n objects, but we only want to arrange r of them, then we have n factorial over n minus r factorial. So the ones we want divided by the ones we don't want, the leftovers. Okay, factorial on both. And that we call n permutations of r. And if you notice on your calculator under that math, right above the exclamation point, you've got that NPR there. So if we pull that up again, I want that behind it. And then I want that. There we go. I can go, if I want, let's do 5 fairy roots, 5, and I want to pick 2 of them. So I go math, I go over to probability, I go down, it's not the exact one above, it's that NPR I want. And then I only want 2. So there's my 20. Okay? So for small numbers, it's easy to do in your head, but for really big numbers, it's nice to have that function on your calculator that will shut that, or will make it quicker to calculate. Okay? Now there are some restrictions. N has to be a positive number and it can't be 0. You can't have 0 objects to pick from. Well, you can. If you have 0 objects to pick from, you can only pick 0 objects. And how many ways can you pick 0 objects from 0? 1 way. So it's not very interesting. But that's your 0 factorial. Okay? 1 way to pick 0 objects from 0. R can be 0. So you could pick 0 objects, but it has to be positive. You can't pick negative objects. So if I have 5 students to choose from, I have to choose between 0 and 5 students. I can't choose more than 5 students, and I can't choose negative 2 students. Okay? And then n has to be greater than or equal to r, which tells me that r can't be more than how many objects I have. I can't pick more objects than I have to start with. Okay? But I can pick how many I have. So I can have 5 objects and pick all 5. If I have 5 fairy roots, and I want to travel on all 5 fairy routes, so I have 5, pick 5. How many ways can I pick 5? Try it on your calculator. 5, pick 5. 5, math. Pick 5. Any guesses before we do it? 120. Why? Why is it 120 ways? Yep.
Because you can do it in different orders.
Right. In different orders. There's only one way that if I don't care what order it is, there's only one way. But I can do it in different orders. So in other words, I have 5 choices for the first fairy and 4 for the second and 3 and 2 and 1. So I have 120 ways. Okay? I'm only going to divide if there's some I'm not picking. Okay? So if I'm picking only 3 ways, then I have to get rid of the other 2. Okay? Make sense? Okay, a couple more examples. When are we done here today? I don't want to run you over time. Friday, 9:40. Okay, we're doing okay, right? We're doing okay. All right, how many students do we have in this class? I can't even remember. Let's see how many we have today. 3, 6, 9, 12, 16, 19, 20, 24 students in our class today. Okay? Let's say in our class we want a president, a vice president, and a secretary. We want to start doing things a little differently in this class. How could we pick a president, a vice president, and a secretary? How many different ways could I do it? Okay. There's 2 ways that I can calculate this, and they're both exactly the same. They give me the same answer. One way is to think about it in terms of the fundamental counting principle. How many picks have I got for the president? 24. Okay? Now, we can't have the president also being the vice president, so how many picks have I got for the vice president? 23. And how about for the secretary? 22. So what's 24 times 23 times 22? That's how many ways that I can order a president, vice president, and secretary in this classroom. And by order, I mean arrange, not tell them what to do. Although that would happen too. So what's...
12,144.
Okay? Now the other way to do that is you have 24 students and you want to pick 3 of them. So you put it in your calculator as 24, pick 3. It will give you exactly the same answer. At least it should, unless we did something wrong in the first one, okay? But it will be 12,144. So you have 2 options for how to do it, okay? In my language, I'm trying to use pick instead of choose. Because did you notice on your calculator here? Oops, under the math button, you've got NPR and you've got NCR. We're going to be talking about NCR next week. And that's different from NPR, so I'm calling the NPRs picks and the NCRs choose. So the P's and the C's line up. Okay, so I'm going to start doing that more. So that's why you'll see I'm using pick. When you think, why isn't she using choose? That's why I'm not using choose, because we're going to save choose for here. Okay? All right. The only other questions that I want to show you are things like this, where we have to solve for unknowns. So let's say I don't know how many objects I have, but I know that if I pick 2 of them, I'm going to get 56 different options. Okay? How many objects did I start with, is the question. Okay. This is where we use our formula. Now, the formulas you don't have to have memorized, because if you look at your formula sheet from the trig, unfortunately there's a trig at the top, so just kind of shade it there if it's making you nervous. But like about 3/4 of the way down, you'll see where it says statistics and probability, I think is what it says. Probability and statistics, and the very first one is NPR. Okay? So NPR is n factorial, so how many numbers we have, or how many objects we had to start with, and how many objects we don't want, which is the difference between the ones we do want and the ones we started with. So for us, we have NPR is 56, and we don't know, but down here we have n minus 56. Okay? Now, there's some different ways you can do this. Yeah?
Why isn't R 2?
Yes.
Oh, yeah. Why isn't it 2? Sorry. I don't know. I don't know. Okay, thank you. Okay? Now, obviously, you could just put this in your calculator and guess. You could just go, what's 5 pick 2? What's 7 pick 2? And just keep trying it until you get the right answer. But I'm going to want to see a little algebra to get full marks for it. Okay? So we set up the equation like this, where n is 56 and r is 2. And then we do some simplifying using this idea here. That n factorial looks like this. Okay? So, whichever one is bigger of the top and the bottom, and it's always going to be the top for permutations, because this is always going to be bigger than this. We're going to go n minus 1, n minus 2, and so on, except that as soon as I match up here with here, I can stop. And I stop, but I remind myself that it keeps on going, and that's what the exclamation mark says, that I would keep going until I hit 1, but I don't have to. Because those match. Okay? So that one would keep going till it hit 1s, that one would keep going until it hits 1, but I don't need to extend those because all I'm trying to do is get them to match so that they cancel, so I have n minus 1 equals 56. Okay? Now at this point, you could do a couple of things. You could multiply that out, bring the 56 over. What kind of an equation would this be? Degree would be 2, so it's a quadratic, right? So we would solve it by factoring. You could do that. Or at this point, you could also do a guess and check here. I want two numbers, n and n minus 1, that multiply to 56. And the numbers are right beside each other. They differ by 1. So what are those two numbers? 7 and 8. So the small one is 7 and this one is 8. So n has to be what? What does n have to be? 8. Okay? So at that point you could do a little guess and check. But I do want to see the algebra that you understand how to simplify factorial notation. And I've got a worksheet for you today to practice that a little bit. Okay? So here's another variation of that same problem. This time you don't know what r is. You know what n is, you don't know what r is. Okay? So you're going to set it up the same way. 20 equals n factorial. This time it'll be 5 minus r factorial. Oh, sorry. 5 factorial over 5 minus r factorial. Okay? Now, do you notice here when we did the canceling, the numbers we're left with are always the bigger numbers. Okay? Because we're canceling smaller numbers here. So it's the two bigger numbers that multiplied to 56. So we want to use that same idea here. 5 factorial is 5 times 4 times 3 times 2 times 1. Some of these numbers, the smaller numbers, are going to cancel with this number to give me 20. Well, to get 20, which numbers do I need to have left behind? The 5 and the 4. So these are the numbers that give me the 20. So the 3, 2, 1 need to cancel with the 5 minus r factorial. So what does r have to be? Not 3. R has to be 2. So that 5 minus 2 is 3. So we have the 3 factorial. Okay? So there is some, not guessing, but there is some places where you don't have to show the work. Like you don't have to go all the way with it, but I do want to see that you understand how that factorial notation brings it into play, where you're not just guessing on your calculator, you're not just guessing 5 pick 1, 5 pick 2. Oh, there's my answer. Okay? You can use that to check your answer, but I want to see a little algebra to show me the work. Questions about that? All right, so